Okay, well, welcome. This is a COVID-19 simulator that has been developed as a way to give you the ability to see how does COVID move through a population. And you have a lot of ability to tweak numerous settings that will give you millions of opportunities to variations to see just how slight changes both in population, geography, people's behavior, the actual virility of the disease, and social changes that are made both through isolation, social distancing, have an effect on how this disease spreads through a population. It's really meant to be informative, and it's not based on any presumption of anything other than what has been released publicly in terms of, let's say, what the population of countries is, where the disease is, and what its death rate is, and how many people are asymptomatic or not, how long it takes to recover, what different behaviors are happening within a population. So this simulation is meant to be graphical. So as you can see right here, right now, this is mostly blank. There are predefined settings um, that you can change, but I've set it up right now just so I do a minimum amount of changing, but I will talk through it. You can set between 100 and 1,000 of population. In the simulation area, it's a box or up to 9 boxes or regions. Um, Simulation as a country or states or cities. We'll go with a single country. 329, I'll make that representative of the population of the United States. We see that it has a percentage of number of people who are infected. If you had more than one region, you have people that travel between the boxes. It doesn't apply in this example, but we would have a percentage of the population that has to be sick before you stop travel between countries or areas. Um, the probability of infection is 15. It's a sliding scale between 1 and 100. We'll give it a 15% possibility or probability of infection. The incubation period is 14 time cycles, and then basically the simulation runs through a cycle every couple of seconds or less. And you'll see it's basically every time uh, the little balls or people move, that can be considered a time period cycle. Do you quarantine the sick? We've turned that off, but if you do, then there's a quarantine zone down here where people basically go in their house or they're in a hospital or somewhere where they are not in the general public and population. Then you can see if you turn that on or off, what kind of change does that make? Um, and there's also a quarantine delay. So, obviously you don't turn purple the moment you get COVID, so it's impossible to really know if you're sick immediately. How long does it take you to order someone or get someone into quarantine? Here it will be 7 time cycles. It won't apply in this example because we're not turning on quarantining. Central location. So that's a simulation of let's say, your local grocery store, where everybody in the community needs to go on a fairly regular basis, weekly, let's say, to go get groceries, to go get food. And so everybody is going there on a semi-regular but not singular time. So all through the time in the simulation, people at random periods of time, these dots will go into the central box on the screen and pick up their groceries and leave. It's a really good opportunity for the spread of the disease because you're in a physically same place. And this simulation shows the spread by having people, when the dots touch each other, that is an interaction that's close enough to transmit the disease. And if you have the lucky fortune of getting the probability of infection, your turn comes up, then you'll become symptomatic or asymptomatic. And we'll get into the percentages of that in a second. To finish this column, the percentage of infected before social distancing is imposed is 15%. So once 15% of the population in the simulation are actively symptomatic or asymptomatic, once you're above 15%, then people social distance, and they social distance by not moving. So you'll find that the majority of the dots on the screen stop moving, and that means they're not interacting with each other. However, like most societies, not everybody has the luxury of just sheltering in place, being at home, self-isolating. People have to go out, and certain jobs must continue to be done. And the doctors need to go to the hospital to work, and the police need to go and protect the city. The firefighters need to fight fires, and you suddenly realize there's a large percentage of people that, even though we may be sheltering in place, there's a large percentage of our population that need to go out and do the work that's necessary to keep society running, even the grocery clerks. So in this example, we have 56% of the population, just over half, will be able to social distance, but 44% will continue to move around and go about their day, whether they need to go get food at the grocery store or go to a job. So you'll see that not every one of the dots stops when social distancing. When the social distancing dot turns green, that means we are social distancing. Not everybody will stop moving, so the disease can and likely will, in some cases, continue to spread. So the death rate here is 1.5%. That seems to be pretty close to a lot of examples we've seen. Obviously, it changes for countries, different countries, and different time periods, but 1.5% may be an accurate number. It's certainly not wildly high or low. And so you'll see that over time, we will have some black dots appearing, and that should be representative of about 1.5%. The travel frequency, again, is related to travel between regions, but it won't be in effect here because we only have one region in this example. But the travel frequency would be 10% of the population would travel at any one time. What percentage of people don't show symptoms? Asymptomatic cases, it's rated right now at 15%. So of the people who are sick, 15% are asymptomatic. The time it takes to recover would be 48 time cycles, which is about 4 times as much as the incubation period. A quarantine delay, again, is not in effect because we don't have quarantining, but it would be 7 time cycles. And the visitation frequency. So what frequency do people have when they're going to the central location? Okay, so it's 15% of the time people are traveling to the grocery store. And again, we've already talked about percentage of social distancing. So we'll start the simulation. What you'll see, there'll be a graph here that shows the entire population, 329, representing 329 million people in the United States. And everybody except one starts out healthy. Obviously, we need to have the disease in the population to begin with. So there's one person who is asymptomatic to begin with. And we'll see how it moves along. And just watch and see how it progresses. So I started the simulation. So you see 329 people are all healthy. We have one person. Oh, they're going shopping. They've gone. The yellow dot there. Oh, bad time to go shopping. We had a super spreader event. That is quite remarkable. Each simulation, even with identical start parameters, and you'll see we've already implemented social distancing. Not everyone can stop work though. This was every single time you run the simulation, there's so much randomness in it that it's quite amazing how starting 2 simulations, one after another, how it changes. And this was quite unusual in that the person who was infected right off the bat went shopping. And this is a very quick deployment of the illness into the population. So as you'll see here on the graph, the green line represents the number of people who are recovering, and quickly people are recovering. And the number of people who are healthy has quickly dwindled to be next to those who have died, the very lowest number. And we still have social distancing in place because we still have more than 15% of the population is infected. The number of people who are asymptomatic is higher than the number of people who are symptomatic, and that's represented by symptomatic people are red, asymptomatic are yellow, and healthy people are blue. And you'll see how it's interesting. The blue line quickly plummeted down, but it's really flattened out. And that is an example of what you've often heard talked about, herd immunity. And herd immunity is a symptom of where you have a large enough population that is far enough spread out that people who are sick um, have less opportunity to actually encounter the healthy. And when that happens, you have a situation where you can have people who are healthy never get sick because they never encounter the disease in enough frequency to actually catch the disease. So as you can see, everybody is moving again because we've now got less than 15% of the population who are infected. We still have infected people out there, and as you can see, the red line in the graph, the infection curve, there's now more people who are symptomatic than there are healthy. Those two numbers have just crossed again, which is quite interesting. And the asymptomatic people are starting to fade out. How this will end, anyone's guess at the moment. It's difficult to be certain. We have at least two people who have died, but it looks like a third person has actually died in the store. There's a black dot covering what should be an orange square in the central location. So we've had 3 people out of the population die, and most people now, almost the entire population, have recovered. We still have some healthy people out there who have been fortunate enough to not catch the disease. The number of people who are sick, we have 2 symptomatic and looks like 3 asymptomatic people still moving through the population. But if this disease fades out, if they don't pass this disease on in fairly short order, then the disease will disappear from the population and the movement will all stop for everyone because the simulation ends. And it'll give you a good idea, does the disease go through the entire population or does it stop? And what percentage of people actually have an opportunity to survive with not ever having encountered COVID? So we still have 1 person who is symptomatic, 3 people who are asymptomatic moving through the population, but rarely, obviously, encountering the healthy. People are still going shopping, going about their day, bumping into each other, and in many cases not knowing who they're seeing. Most of the people they encounter are healthy, unhealthy, but if you watch a red dot or one of the yellow dots, you'll see occasionally they bounce into a blue dot, and that's how the disease can continue to move through this population. And it may end very quickly here, or it may continue to propagate just based on the randomness of the dots. And occasionally you'll see one of these red or yellow dots bouncing into a blue dot. And if the numbers come up wrong, the disease moves on. If it doesn't, then it will fade and our simulation will end. This has been an excellent example of a super spreader event, this simulation, because the 1 sick person at the very beginning who was moving through the population went to the central location, to a church service or to a hockey game, or they went to the grocery store, somewhere where they, as you saw early on, all these asymptomatic people came out of the central location. It was remarkable. That is an aspect of the simulation. I've watched hundreds of these already in preparation for this video. It's never happened before, so it was quite interesting to be able to capture it on this video. It looks like we have 1 asymptomatic person moving through the population. If they recover before they pass on the disease, the simulation will stop. But you've seen that that yellow dot has bounced into a couple of people who are healthy. Did they pass on the disease, or will it fade from the population and be nothing much more than a bad memory of 2020? We'll see, because the time is running out on this asymptomatic person. I only see 1 yellow dot still on the simulation. But there's even fewer people now. Our graphs, as you can see on the bottom left, are really stable. The populations aren't really changing. And everyone does recover from COVID eventually. the disease does go to a point of, in this simulation, to a point of healing. So, or recovery, I guess is the best term for it. We continue to just have 3 people who have died in the simulation, which is, people are certainly not wanting to die, and it's a terrible thing when it happens, but it's not everybody in the population. Oh, that yellow guy just rubbed shoulders with somebody who is healthy. Will the disease move on, or will it stop? I can only see one person who is asymptomatic in this simulation. And oh, another bounce. Did they pass it on? As you can see, this is how a disease can continue through a population for a very long time without actually ever fully going away, because even though there is only a small handful of healthy people and one asymptomatic person, they're having an awful lot of success in rubbing shoulders, getting on elevators, sitting next to people in coffee shops and restaurants. Did they pass it on? Because they don't have any obvious symptoms. They are asymptomatic. Oh, now they've turned symptomatic. The disease has progressed for that one person. That's a not fun experience. And just rubbed shoulders again with another healthy person and another healthy person he passed it on to. So it's almost like a sports game here. We see that the torch has been passed from the asymptomatic person, and he touches another a blue healthy person. A lot of close calls, and now he's recovered. Unfortunately, the disease did get passed on, almost like a successful pass in football, where the asymptomatic person is running down the field, uh, almost in a safe area, if you will, without anyone healthy and unrecovered. But there, oh, another encounter with a healthy person. Did it get passed on? It doesn't appear to have been passed on, but we'll see if this disease does fade away for this one last person who is sick. So it almost feels like I'm calling a sports game. Or will this asymptomatic person be the very last? Oh, another encounter with a healthy person. Will the disease get passed on yet again and continue through the population, dragging on the scourge of COVID-19, or will it be the end? We'll see here shortly if it actually did get passed on, because the actual transmission time when people are asymptomatic in this simulation is rather short. So it's not like they go along blue for a long time before they'll turn yellow. They'll turn yellow pretty much immediately if they're unlucky in the numbers. Or will this asymptomatic person recover? Oh, another encounter, another lucky fellow. We'll wonder if the asymptomatic person ends up shopping too. That's another dangerous thing, although so few people now are sick. Oh, another encounter. It's amazing, and another one. It's amazing when you think there are so few people who are healthy and never and have no immunity to COVID. This is assuming that there is no vaccine, as it is right now in July 2020. That a single person moving random through the population, not deliberately trying to infect others. Again, this yellow dot is someone who is asymptomatic, does not show any signs of the disease, does not feel ill, doesn't have a cough or any breathing problems. This person is going about their lives thinking, I'm one of the healthy ones. I'm a blue dot, I think. They're not. They're actually moving about, spreading the disease at the rate that COVID does spread and has been shown to spread. In this simulation, it's now stopped. So he got better and never knew he had it, but now we're in a situation where you can see we had 3 people die, and we had the vast majority, over 300, catch the disease and recover. And if I count quickly, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 people out of a population of 329, so about 5% didn't catch the disease. That's a randomness because we can run it immediately again. We'll reset the graphs and you'll see it will run differently. Now you may be interested. You can download this code for free. It's available on a site called GitHub, and the links are in the video, so you can link to it. You will need a copy of a programming language called Python, and or know somebody who can get it to run. It's totally available, open source. You can see the code that made it run and tweak it for your own joy and pleasure and information. Because really, if you want to come and see all the different values that we can change, this video is getting long, so I will stop here. But I'll put up other videos where I actually demonstrate where you can see how travel between different regions really has an effect on the spread of COVID, of any disease really, and can perhaps give you an understanding as to why many of the social effects of lockdowns and of travel bans were brought in, because it does make a difference. Thanks for watching.